Alrighty, let's get started for today. Well, last class, we started into the topic of fluids. And so just to review what we went over, the main equation that we're going to be using for this part of the topic is called Bernoullis Principle or Bernoullis Equation. And what it is a relationship. And the way we're going to be using it is in the form of pipe systems. So you have a system of pipes that you're going to send fluids through, let's say water pipes going to a house. And this pipe system will have water flowing through it with a certain velocity. So maybe it's being pumped from a water station or however it's being pumped, water's coming in. The pipes can change sizes, so they can constrict, they can expand, they can change locations, so they could go from the first floor up to the second floor or down into the basement, all sorts of stuff. And the questions that we may want to ask about are things like, when the pipe goes from here to here, what is the change in the pressure, the water pressure in the pipe? Or if the pipe constricts to this new size, how fast will the water be flowing through the pipe? Things like this. And so the equation is an equation of pressure. It's a relationship of the pressure, and it's got multiple terms in it. Each term tells you about the pressure in the pipe due to some specific physical characteristic. And so what I mean by that is, first of all, you have the actual pressure. Maybe this is how hard the pump, the water pump, is pushing the water through the pipe. Then you have a term for the pressure due to how fast the water is flowing. And this term is 1/2 rho V1 squared. Well, remember, rho is the Greek letter. It stands for density. So that tells you what type of fluid are we talking about. Is this water? Is this oil? Is this natural gas? What fluid are we sending through these pipes? And then you have another term which tells you how the pressure changes due to the fact that the pipe system changes height. It goes up, it goes down, all sorts of stuff. And that term is a rho times G times H. And so this set of terms, when added together, gives you the total pressure in the system at a certain location. So it's like you're testing all the characteristics at one point, and then the pipe system moves along, goes to some other location, and then you're going to test the same characteristics at the other location. And it turns out that if you add all the terms together, that total pressure will be the same everywhere you check. And so we say it's equal to P2 plus 1/2 rho V2 squared plus rho GH2. Okay. So this equation is very, very similar in nature to conservation of energy, where you have initial kinetic plus initial potential is final kinetic plus final potential. And so what we had there was the total energy of a system at some location is the same as the total energy of the system at some other location. But the energy itself could be separated into different pieces, kinetic and potential, and how much of the energy is kinetic versus how much is potential can change. But when you add them both up together, you always get the same number. Okay, so very similar relationship. And then we had a second relationship that became important, because if you notice in this particular equation, Bernoullis equation, we have a term that deals with the speed or the velocity of the fluid flowing through the pipes. Well, we may want to know how the speed changes based on something we can measure. And the thing we can measure that does affect the speed of the fluid flow is the size of the pipe. And the example we used to prove this was sticking your thumb over the end of a hose. When you just have a hose open, the water's coming out and the water shoots out a certain distance. But then you put your thumb over the end of the hose and all of a sudden the water is able to shoot out a lot further. Well, the reason that's true is because as water is flowing through the pipe, the thing that has to stay constant is not how fast the water is flowing, but rather how much water flows per second. So in other words, if you have, let's say, a pipe and you have water flowing through, let's say you have 1 gallon of water per second flowing through or coming into the pipe, let's say, you're getting a gallon per second coming in. Well, a gallon per second better come out. Because if not, then that means somewhere in the pipe, there's a holdup. And if there's a holdup, that means a lot of water is being backing up. And if this continues on for a long period of time, obviously enough water will back up that it'll burst the pipe. The water had nowhere to go and it eventually becomes like a bomb. Well, thankfully, that's not what happens. Rather, what happens is that whatever amount of water comes in must come out in the same period of time. And in order for that to happen, if we have a situation where the pipe size changes, it constricts, let's say, well, less water seemingly would be able to flow through the smaller part of the pipe per second. So to accommodate this, the water speeds up so that even though the size of the pipe is now smaller, because it moves faster, you get the same amount of water coming out as you had coming in. And so this shows us that there's a relationship between the size of the pipe and the speed of the fluid. And that relationship is called the continuity equation. And what it says is quite easy. It says that the volume flow rate or the mass flow rate, and all that means is how much water flows per second. The volume of the water that goes through the pipe per second is constant. No matter where you check, if you have a nice closed pipe system, if you check how much water is flowing per second in this location, and then you check in some other location, it'll be the same number. And that number is A1 times V1. That is the area of the pipe, the cross-sectional area, how big is the opening at one location, times how fast the water flows there, must be equal to the size of the pipe times the velocity of pipe in the second location. Okay, so this is the volume flow rate is constant. That's what this equation is saying. Where A times V is the volume flow rate. Because if you think about it, A, well, that's meters squared. V, that's meters per second. So meters squared times meters per second is meters cubed per second. Meters cubed is a volume, and of course seconds is time. So this is the volume flow rate, how much volume is going per second. And so it's the combination of these two equations that will allow us to solve the problems we're going to have, at least for this first part of fluids. You're going to be given a pipe system. The pipes can change size, they can change locations, all sorts of stuff. And we may want to calculate something like the difference in pressures from this point to this point. Well, in order to do it, we'd have to, of course, solve Bernoullis principle or Bernoullis equation. But one of the issues we're going to run into as we do examples is that we may not know the velocity of the fluid in the second location. Maybe we're given it in the problem for the first location, but certainly we would have to figure it out for the second location. And the way you would figure it out would be to use the continuity equation. So that's what we're going to see when we do examples. Now, before I get to examples, I do want to go over one phenomenon that is, relatively important and a big example that's always discussed when Bernoullis principle is talked about. And that is about flight. One of the big areas people usually are introduced to Bernoullis principle is when the question of how an airplane stays in the sky is possible. And so to do this, let's look at Bernoullis principle first. If we look at Bernoullis equation, it's got three terms in it: pressure itself, then we have a term about the velocity of the fluid, and then we have a term about the height, the depth. How high does the pipe go or how low does it go? And one thing we're going to do is when we're solving Bernoullis equation type problems is if our problem doesn't have a difference in one of these terms. So let's say we have a pipe system that doesn't go up to the second floor. It just remains on the bottom floor. So the height doesn't change. Well, in that case, we don't have to worry about rho GH. If H1 is the same as H2, then those two terms will just cancel out. So we don't even have to worry about them. And the same, of course, goes for the velocity term. If we have a pipe system that doesn't change size, if the pipe is just a pipe and all it does is go upstairs or downstairs, well then, if the pipe doesn't change size, the fluid doesn't change its velocity. So V1 is the same as V2, and we can ignore that term. Okay, that's just generally true. Well, let's look at the case where the height doesn't change. So we start with Bernoullis equation and we get something that looks like this. P1 plus 1/2 rho V1 squared is P2 plus 1/2 rho V2 squared. Okay. Now let's consider something. Let's consider if V2 is bigger than V1. That is to say, if we have a fluid flowing through a system and the fluid speeds up, so it was moving at a certain velocity and now it's moving faster. The question is, what happens to the pressure? Does the pressure go up or does the pressure go down? And the way we could see it is this. Take the first two terms, the left side of the equation, these two terms here. Whatever they are, it doesn't matter. We'll get a number. Let's call the number alpha, okay? 500, whatever it is. And I know on this side, when we add them up, we get the same number alpha. That's also 500. However, if that's true, but I know that V2 is now bigger than V1, so that the second term on the right side is a bigger number now. Well, in order for that term to be bigger, but the right side to stay the same, P2 must be less than P1. Right? So for instance, the left side, let's say P1 is 300 and 1/2 rho V1 squared is 200, as an example. So we add them up and we get 500 for the left. And I know on the right, we're going to get 500 as well. But if the second term, 1/2 rho V2 squared, is now 400 because V2 went up, well, the only way for the right side to be 500 is if P2 is now only 100. Right? So 100 plus 400 gives us the 500. And so you can see P2 is now less than P1. Okay, so what does this tell me, generally speaking? What this tells me is that if you have a fluid system, a flowing fluid, if the fluid speeds up, then the pressure in that part has gone down. So a faster moving fluid has a lower pressure. A slower moving fluid has a higher pressure, all else being equal. Okay, so if that's true, if V2 is bigger than V1 implies that P2 is less than P1. If you move faster, you have a lower pressure. Then we could figure out why airplane wings are designed the way they are. If you've ever seen an airplane wing, let's look at it from the side, from the edge, not from the top or anything like that. So if we're looking, here's the airplane with my poor drawing, and here's the wing. Okay. So if we're looking this way at the wing from that direction, what we see is the wing looks like something like this. Bottom's flat, and the top is curved like this. Okay, something like this. It's a crude drawing, but it's basically this shape. And the reason it's shaped like this is because the fluid in this system is the air. Remember, fluids in physics can be gases or liquids. And so the air in the atmosphere, the air that the airplane is trying to travel through, is the fluid for our system. And as the airplane, of course, is flowing this, or is flying this way to the left, let's say, the air going over the wings, coming in, here's the air coming in. Well, on the bottom, it just goes straight underneath, but on the top, it follows this other curvy path like that. Okay. Now, if this is true, notice the path on the bottom, this nice straight path, is shorter than the curved path on top. Because, of course, the shortest distance between 2 points is a straight line. Here, the bottom is a straight line, but the top is curved. And if it's curved, that means it must be longer. It must be a greater distance. So the path on top is longer. However, in order for us not to have weird effects, the air that goes over the top and the air that goes underneath the wing must reach the other side of the wing at the same time. Okay, so it's not like the air at the top takes longer to get to the other side since it has to go a bigger distance. It doesn't. The air gets to this point at the same time that the air on the bottom gets to that point. Now, the only way this is true is if the velocity up here, let's call it V2, is on the top and V1 is on the bottom, the speed of the air flowing underneath the wing versus the speed of the air flowing over the wing. If the air over the wing has to go a bigger distance in the same amount of time, then its speed must be bigger. So V2 must be bigger than V1. But we already know if the velocity goes up, then its pressure goes down. So that means for our airplane wing, since the speed of the fluid flowing over the top of the wing is bigger than the speed of the fluid underneath the wing, that means the pressure on the bottom of the wing is bigger than the pressure on the top of the wing. And what does that mean? That means as pressure, the air is pushing up and the air on top is pushing down. Okay, that's the pressure due to the fluid. It's pushing on the wing. On the bottom of the wing, it's pushing up. On the top of the wing, it's pushing down. But if on the bottom of the wing, the pressure is bigger, that means there's more force underneath the wing that's pushing up than there is force pushing down from the top. Well, if there's more force pushing up from the bottom than from the top, pushing down, then there's a net force pushing up on the wing. It's like, well, you lift with 500 pounds of force, but the weight is only 400 pounds. pushing down. Well, that's 100 extra pounds you're lifting up, so the thing's going to go up. And that's exactly what happens. There's an extra force called lift being applied to the airplane wing, which is pointing upwards because the pressure on the bottom of the wing is bigger than the pressure on the top of the wing. Why is it bigger? Simply because the speed of the fluid moving underneath the wing is slower than the speed of the fluid over the top. Over the top, it has to go a bigger distance since it's curved. So the water or the air had to speed up to make up that distance. And if you have a bigger speed, you have a lower pressure. So more pressure on the bottom, less pressure on the top. That means more force from the bottom than the top, which means there's a net upwards force on the wing. And if that net upwards force is bigger than the weight of the plane itself, then the airplane is lifted up off the ground. If the force isn't big enough, if the weight is bigger than this excess force, then of course the airplane doesn't lift up off the ground. It just sits there on the ground. But if you can move fast enough to make this difference in velocities big enough, then there's going to be extra force, enough extra force from the bottom to overcome gravity, and thus you'll lift up the airplane into the air. Okay, so there's a physical representation of Bernoullis principle. One, or at least one of the things we could take away from Bernoullis principle, which is all else being equal, if you increase the speed of the fluid, you will decrease the pressure in the fluid. And so we take advantage of that fact. We design our airplane wings to allow for this to be true or to maximize this effect, and thus we get lift. Are there any questions about that? Just as a conceptual idea. All right, well, with that, now that we've seen kind of an interesting way Bernoullis principle can manifest itself, let's try some example problems, actually working out real problems. So let's take this as an example. Let's say we have a pipe system. You have a pipe. Oops. Of radius 20 centimeters with water flowing through at a speed of 10 meters per second. The pipe then constricts to a radius of 15 centimeters. Calculate the change in pressure. Okay. So there's a nice typical example of a Bernoullis principle style of question. You have a pipe system, fluid is flowing through the pipe, and the pipe does stuff. It can change size, it can change locations, things like this, and we want to know about the pressure in some way. All right, well, first thing I'll do is go ahead and draw the picture just so we get kind of a visual idea of what's going on. We have a pipe of a certain size. There it is. And I know the size of the pipe, the radius at least, R1 is going to be 20 centimeters. But remember, in physics, unless otherwise stated, distances better be in meters. So I have to convert 20 centimeters into meters. So it becomes 0.2 meters. And we've got water flowing through my pipe. And I know the water is flowing with a velocity of 10 meters per second. Then, sometime down the line, the pipe constricts to a new radius. So it constricts, becomes smaller. And I know in this part of the pipe, the radius now, R2, is 15 centimeters. So again, converting to meters, that becomes 0.15. And we have the fluid flowing through this part of the pipe, but we don't know its velocity. We're not told in the problem, but that's okay. This is everything we know. And what is it I'm looking for? Well, the change in pressure, that's a capital P, not a little p. We could call change in pressure P2 minus P1, right? The difference in pressure. It was something, now it's something else. You take the difference between those, that's how much it's changed. So when you see change in pressure, think P2 minus P1. All right, so there's my problem. Every time you see one of these pipe system type problems, first thing you could think of is Bernoullis equation. So we write it down, P2 plus 1/2 rho V1 squared. P2, my lord. Starting with P1, sorry. Plus rho GH1 is P2 plus 1/2 rho V2 squared plus rho GH2. There we go. There's Bernoulli. One thing I know is as I read this question, I don't see anything in the problem about the pipe changing heights. I don't see anything about it going to the second floor or it dropping down 10 meters or anything like that. There's nothing in this problem about a change in height. And so I could just ignore the term that has height in it because they would cancel out. If H1 is the same as H2, then rho GH1 is the same as rho GH2. So when you plug them into the equations, they would cancel out. So I just ignore them. So all I have left is what's there. The next thing I want to do is go ahead and solve the equation for what it is I'm looking for. I'm looking for this, P2 minus P1. So use Bernoulli's equation and get P2 minus P1 on one side. Everything else goes on the other side. So, okay, P2 is already there. So let me bring P1 over to this side. And I'll move this 1/2 rho V2 squared over to that side. Get P2 minus P1 by itself on one side. Everything else goes on the other. So I have P2 minus P1 equals, on the other side, 1/2 rho V1 squared minus 1/2 rho V2 squared. Okay, so just a little algebra. P1 goes on the other side of the equation, becomes negative, so P2 minus P1. And then 1/2 rho V2 squared, I need to get it over to the other side, so he becomes negative. So you have 1/2 rho V1 squared minus 1/2 rho V2 squared. So that's what I want to solve. That's delta P. That's what I want. So I need what's on the right side. Do I know the numbers on the right side? Well, rho, that's the density of water. Now, I'm not told in the problem, but this is something you'd be given on a test or something. So just know rho, the density of water, is 1,000 kilograms per cubic meter. Okay, it's just a number, 1,000 for water. So I know the density of water, rho, fine. I know V1 is 10, but I don't know V2. And so, okay, this is going to be something you're going to find a lot in the topic of fluids as we do more and more problems and we learn more and more theory, is a lot of the problems in fluids deals with, here's the equation I want to solve. And in order to solve it, I need to know all of these terms. Some of these terms I won't know, and so I'll have to do some side calculations to try to calculate those terms. Once I've calculated them, then I plug them back into my main equation to actually get my answer. And so when I'm looking at this, what I see is I have everything except for V2. I need V2 to be able to solve this. So I'm going to do a side calculation to try to calculate what V2 is, and then I could go back and plug it in and get my answer. So how do I get V2? Well, remember, the second equation we have here is called continuity equation. And the continuity equation is the equation that tells us how does the speed of a fluid change due to the size of the pipe. So continuity on the side, A1 V1 is A2 V2. When you think about a pipe, the pipes that we're going to be dealing with are the nice circular cylindrical pipes. So that means the hole, the opening in a pipe is a circle. So when you want the cross-sectional area of your pipe, that's pi r squared. So this equation becomes pi r1 squared, that's A1, times V1 is pi times r2 squared times V2. Okay. Now notice pi's cancel. There's a pi on the left, there's a pi on the right, so they cancel out. And in fact, they will always cancel out. But the reason we always write it is because if we didn't write it, R1 squared V1 is kind of hard to remember, but A1 V1 is easier. So if we remember A tells us it's pi r squared, but the pi's go away. So that's how we get the actual question or the actual equation. But doesn't matter. Even if you included the pi, if you didn't cancel out the pi, you'll still get the same answer. It's fine. But to save yourself some time, just remember pi cancels here. And so what we have is R1 squared V1 is R2 squared V2. Solve for V2. V2 is R1 squared over R2 squared times V1. Okay, just a little algebra. I move the R2 over to the other side. It goes in the denominator. So there we go. That's how I could calculate V2. Now all I need are these numbers. Do I know R1? Yes, I do. There's R1 sitting there. R1 is 0.2. So 0.2 squared. Do I know R2? Well, let's look up R2. There it is. 0.15. 0.15 squared. Do I know V1, the velocity of the fluid in the first part of the pipe? Yep, it's 10. So I'll plug it in, 10. And perfect. I got a nice equation. I know all the numbers in the equation. So all I have to do now is plug this stuff into my calculator and I'll get my answer. And if I do that, 0.2 squared over 0.15 squared times 10, I get 17.78. Now, first of all, are there any questions about this? About how I did that part? Figuring out the velocity in the second part of the pipe. All right, can anybody tell me, by looking at this number, can you tell if it's right or wrong?
No. How exactly would we be able to tell?
Okay, man, that was kind of a stupid question, wasn't it? How about this? Can you look at the answer and tell if it's definitely wrong? Do you think it's wrong by looking at the number? Or does it make sense? Does it look okay? That's more what you can do. You can't look at it and say, oh, it's definitely right. But what I could do is, if it were wrong, I could look at it and tell it's definitely wrong. And I'll explain it if no one can, but I just want to give an opportunity. Can anybody look at it and give me an idea if you're going to kind of quickly check yourself to make sure at least it makes sense? Okay, well, obviously this is our first example, so I don't expect everybody to have every answer yet. When I look at this number, I'm first asking myself, remember, and this is true for everything you do in physics and even if you're not going into physics and some other science, it's very important to do this. Always have in your mind when you're solving a problem, the problem itself. What is it we're doing? What does this stuff actually mean? I'm not just a mechanical device that's pumping out answers unthinkingly. The reason, physicists are involved in this stuff, and it's not just pure computer work, is because the physicist has a brain, and we could use our brains to actually figure out or think about things to make sure they make sense. In this part, just talking about the speed of the fluid, what do I have? I have a pipe. The pipe constricts. What do I know about the speed of a fluid when the pipe constricts? Does the speed go up or does it go down? Anybody remember?
It increases.
It increases, that's right. And remember, the way I remember it is if you put your thumb over the end of a pipe, the pipe is as if you constricted the pipe, and the water shoots out a lot faster and shoots out further. So when you constrict the pipe, the water speeds up. Well, here we constricted the pipe. It went from 20 centimeters down to 15 centimeters. So I expect the velocity in the second part of the pipe to go up. It should now be moving faster because we're in the constricted part. And so I look at my work. I say originally the speed was 10. Now it's 17.78. It went up. Perfect. It seems okay. I can't tell if it's right. I still may have made a mistake in my calculator, but at least looking at it, it makes sense. If this number would have been 7.78, then I can immediately stop and go back and see where I made a mistake, because I know the speed should have gone up, and so I should have a faster velocity rather than a slower velocity. But here I have 17.8, perfect. It seems to make sense, so I can move on to the next part. Remember, this calculation is purely to get V2, something I needed for my actual equation. Now that I have it, I go back to my Bernoulli and I say the change in pressure, the thing I'm looking for, is 1/2 rho V1 squared minus 1/2 rho V2 squared. Plugging in the numbers, I have 1/2, rho is 1,000, V1 was 10 squared, minus 1/2, rho is 1,000, V2 is 17.78 squared. And now I have the equation with all the numbers plugged in, and I can calculate the number. So when I go calculate this number, let's see, I get minus 108,064.2, or what you're going to see a lot in fluids is the numbers are kind of big. And so a lot of times we use scientific notation just to make it a little nicer looking. So if I were to do this in scientific notation, it's minus 1.08 times 10 to the 1, 2, 3, 4, 5 pascals. Either one of these numbers is fine for the class. Scientific notation or no scientific notation, doesn't matter to me. But there's the answer. Now, I get a negative And is that okay? Is it okay to get a negative number, or should it be positive? Well, remember what we're being asked. How does the pressure change? Well, the fact that I got a negative number just means the pressure went down. It was at a certain pressure. It's now this much less than it was before. Okay. If the answer were positive, then it means it's this much more than it was before. So I don't know what the actual pressure is. I don't know what P2 is. But what I know is whatever P2 is, or whatever P1 is, P2 is 1.08 times 10 to the fifth less than P1. And so that's why we get a negative number. The pressure went down. And again, does that make sense? Well, it should make sense because I just said when we talked about flight that when the velocity goes down, when the velocity goes up, the pressure should go down. And indeed, that's what happened. We constricted the pipe. The constriction in the pipe made the velocity of the fluid go up. So now the fluid's moving faster. And thus, if the fluid is moving faster, the pressure in the second part should be less than the pressure in the first. And indeed, when we calculate the change, we find that it's a negative change. The pressure went down. So everything is connecting. Everything is making sense if I want to check my answers instead of just boxing them. But that's a nice typical Bernoulli style problem. We start with a system, a pipe, fluid in the pipe, and we know some stuff about the pipe. The pipe changes. Maybe it constricts, maybe it goes up to the second floor, something happens. And the question is, in this case, find the change in pressure. Well, Bernoulli, because we have a pipe system and we're talking about pressures. So I write down Bernoulli. I also, if the question doesn't have it, I'll go ahead and draw it out myself just to remind me of all the details. I keep only the terms that are important. In this case, because the height didn't change, I could just get rid of the height terms, and I kept everything else. And I algebraically modify Bernoullis equation to calculate what I want. In this case, I want change in pressure, so I move things around till I get P2 minus P1 by itself. Then I say, okay, on the right side of the equation, what is everything I need? Well, I need rho, I need V1, and I need V2. Rho I know, because I'm told this is water, and I know the density of water. V1 I know, because it's given in a problem, 10 meters per second. But V2 I don't have. So there's something I need to go calculate on the side. So I take a detour, and I now calculate the speed of the fluid in the second part of the pipe. How do I do it? I use continuity equation. So I set up the continuity equation over here on the side, plug in all my numbers, making sure I've converted my units correctly. Remember, everything's in meters and all of that. And I get my speed, the new speed. I say, does it make sense? Should it have gone up or should it have gone down? In this case, it should have gone up. And indeed, that's what I get. So I could accept it. And I go back to Bernoulli and say, now I know V2. I have all the answers I need to plug into this equation. So I now have Bernoulli, plug in all the numbers, use your calculator, and you get an answer. The answer can either be in scientific notation or not, depending on how you want to write it. But there you go. So are there any questions about this example?
So just going over like the relations between the relations between the variables again, right? So then your pressure has an inverse relationship, or the change in pressure has an inverse relationship with the velocity, or change in velocity, I guess, right? Because if the first velocity in this one was 10, the second one was 17.78, and then your answer was negative. So if velocity 2 is greater than velocity 1, your pressure is going to be negative, or change in pressure is going to be negative. And that makes sense. Yeah. Okay.
Right. And that's exactly what we saw when we talked about the flight thing. Mm-hmm. When you increase the velocity, the pressure decreases.
Gotcha.
Yeah. Perfect.
All right. Cool. Just want to, yeah.
Yeah, and that's what you're going to find. As I said, it's not just here in Bernoulli, but also the next big topic in fluids that we're going to get to is Archimedes' principle. And Archimedes' principle has a set of 3 or 4 relationships that are all kind of like that, where it's like, okay, uh, the buoyant force acting on an object is related to the volume of the object, and the volume of the object is related to this. And so you have to keep in your mind, how are all of these things related? Because for a given problem, you don't know which relationship you're going to need. For Bernoulli, it's helpful to always have in your mind, when you constrict a pipe, the velocity will go up. When you expand a pipe, the velocity will go down. That's the first. And then also along with that, when the velocity goes up, the pressure goes down. And when the velocity goes down, the pressure goes up, of course. And so when you have those in your mind conceptually, then when you start actually calculating real numbers, you can kind of check yourself along the way to look out for any mistakes, instead of having to go all the way back through the problem and try to check in some other way. It's kind of a quicker way of just making sure there's not something glaringly obvious that's wrong. Any other questions about this example? All right, well, I'll go ahead and leave it here for today. I'll give y'all a chance to get out early. Next class, we're going to do more examples. And in fact, this particular example was a little bit simpler because we were able to get rid of one of the terms, the height term. So next time, of course, we'll do examples where all of it is necessary, where the pipe is not just going to constrict or expand, it's also going to change heights. And so it's the full-on Bernoulli stuff. But if you can handle what we did here, certainly that's going to be the same type of thing. It's just we're going to have 2 extra terms in the equation with more numbers. But the same kind of process is going to be followed. You start with Bernoulli, you algebraically move it around to calculate what you want, and then you look on one side of the equation, what are all the terms I need? If I have all the numbers, I just plug them in and get my answer. If I don't have all the numbers, then we're going to have some side calculations to do, like the continuity equation, to get those numbers we need. Once we've gathered all the numbers, then we just plug it into the equation with our calculator and get an answer. Okay, so next time, more examples. Make sure we actually understand it well. On Canvas, you'll have the practice problems with solutions posted, and some of the old lecture, like the lectures from last year, where I discussed fluids then, will also be posted. So if you want to move ahead, look ahead at some of the stuff we're going to be getting into, or to try to get some more examples just on the side, if you have some free time to look at it, you'll be able to find all of that on Canvas. But unless you have any questions, you are free to go for today, and I will see you on Thursday.
Good morning. I had a question, but it was related to Gen Physics 2 course.
Okay, sure, no problem. What's up?
There was an assignment that was due on Friday.
Yes.
And I wasn't able to submit it because I had left for a track meet on Thursday. And
Okay.
so I was wondering if I could possibly have the opportunity to submit it.
Sure. Go ahead and email me to let me know and to remind me, and I'll go in and extend a deadline for you. And then I'll send an email to let you know when it's done.
Okay. Thank you.
Sure.
Oh, actually I have one more question as well. Well, I guess I could just email you as well. I needed to set up an advisor meeting.
Yeah. Okay. Yeah, definitely. In the same email, do that, and I'll let you know what free times I have to get the advising done for sure.
Okay. Thank you.
No problem.